Okay, I want to start today with a bit of a philosophical puzzle.
Oh, I like a good puzzle.
Right. So imagine you're studying for a test, a really big test.
Right.
You spend weeks reading, highlighting, making all these deep connections, really understanding the
The
material.
struggle phase.
Exactly. Your brain is just it's lighting up, forming these complex webs of knowledge. But then you sit down for the actual exam, and it's multiple choice, A, B, C, or D.
A dreaded bubble sheet.
Bubble sheet. You have to take all of that rich, complex understanding and just collapse it down to filling in a single bubble.
Hmm.
Now, if I'm an alien scientist trying to figure out human intelligence, what tells me more? The filled-in bubble sheet or your brain activity the night before.
I think we'd all agree the real intelligence is in the struggle, not the bubble.
Right. But here's the paradox we are unpacking today. We've built these massive AI models, large language models, and we've basically designed them to do nothing but fill in bubbles. Their entire goal is to predict the next word.
Correct. It's all about minimizing what's called surprisal. That's the mathematical goal.
But a new paper just dropped that suggests we've been looking at this completely wrong. It turns out when you compare these AI models to a human brain, the part of the AI that's best at predicting that next word, the expert test taker, it looks nothing like us.
It's a fascinating disconnect.
The paper is called Abstraction, Induces the Brain Alignment of Language and Speech Models. It's a preprint from Chang, Vidia, and Antonello. And their big find is that the magic, the part where the machine actually aligns with our brain activity, it isn't at the end. It's in the messy middle.
The middle layer mystery. Yeah. And it really challenges the dominant story in neuroscience right now. We're going to have to talk about predictive coding, and we'll need to break down a concept called intrinsic dimension.
I love it. So let's get into the setup. This wasn't some hall experiment, was it?
No, this was comprehensive. They looked at a whole suite of models. On the one hand, you have text-based LLMs, things like Pithy at OPT, but they also looked at speech audio models, AIs that process raw sound, like WaveLM and Whisper.
And what about the human side of the equation? What were they comparing all this AI activity to?
They used a fantastic data set of humans listening to stories, specifically stories from the Moth podcast.
Oh, that's a great choice because it's not dry technical stuff. It's storytelling. It has emotion, pauses, slang. It's messy.
It's real. And they had two kinds of brain scans. They had fMRI, which measures blood flow, so it tells you where in the brain things are happening.
Right, the spatial map.
And they had ECOG, which is electrocorticography.
That's the one with the electrodes directly on the brain, isn't it?
Yes. It's invasive, but it gives you incredible timing. You know when the neurons are firing with millisecond precision.
Okay, so you've got the human listening, the AI processing the exact same story. And the researchers are basically trying to build a translator between them.
Exactly, an encoding model that looks at the numbers inside the AI and tries to predict the brain activity at that exact same moment. And they did this layer by layer.
Let's clarify layers really quick. We talk about these models as a stack or like a layer cake.
Yeah, that's the best way to think about it.
Yeah.
The data, a word, a sound goes in at the bottom, layer 1. It gets processed, passed to layer 2, then layer 3, and so on, getting more and more refined until the final layer spits out the prediction.
So my assumption, and I think most people's assumption, would be that as you go up the stack, the AI gets smarter.
Sure.
It understands more context. So logically, the match with the human brain should just go up and up, and the final layer should be the most human-like.
That is the logical assumption.
Yeah.
But the data says the complete opposite.
Walk us through this middle peak they found.
So when they graphed the brain alignment, how well the AI layer predicted the human brain activity, it made this inverted U shape.
Okay.
It starts low in the early layers, which makes sense. Then it shoots up and peaks, right in the intermediate layers, middle of the model. And then as you get to the final layers, the alignment actually drops.
It drops.
Significantly. For some models, the final output layer is way less brain-like than the layers that came right before it.
That's wild. It's like the brain is interested in the thinking, but not the final answer.
Precisely. And this is where we run headfirst into a conflict with the very, very popular theory called predictive coding.
I feel like I've been hearing about that for years. It's the idea that the brain is basically just a prediction machine, right?
That's the gist. The brain's main goal is to minimize surprisal.
Is surprisal a real word?
In information theory, yeah. It just means how unexpected something is. If I say, the sun rises in the glass.
Low surprisal.
Right. But if I say, the sun rises in the spaghetti, that has very high surprisal.
Got it.
And the theory is The brain wants to be bored. It wants to predict everything perfectly. Since we build LLMs to do the exact same thing, guess the next word, everyone just assumed that's why they look like brains. We predict, they predict, so we must be the same.
But this paper measured surprisal, too.
They did, for every single layer. And, no surprise, the AI gets better and better at prediction as you go up the layers. The final layer is the absolute champion, lowest surprisal.
So if predictive coding was the whole story, that final layer should match the brain best.
It should, but it doesn't. The middle layer matches best, and the middle layer is just kind of mediocre at prediction compared to the end. In some models, they even found a negative correlation.
Negative.
Yes. In the later layers, as the model got better at predicting the next word, it actually got worse at looking like a human brain.
That is a staggering finding. It's like saying to think like a human, you have to stop trying to be right all the time.
Or at least stop trying to narrow everything down to a single answer. It suggests the brain-language network isn't optimizing for the bubble sheet. It's doing something else.
So if the hero of this story isn't prediction, what is it? The paper proposes this new mechanism, meaning abstraction, and they use a metric called intrinsic dimension, or ID dollars. You have to break this down for us.
I do. The word dimension makes people think of sci-fi, but in data science it's simpler. Think of it as degrees of freedom.
Okay.
Imagine you're walking on a tightrope. You can only move forward or backward. That's a low-dimensional space. One dimension.
Right. Not many options.
Now imagine you're a bird. You can go north, south, east, west, up, down. You have way more freedom. You're in high-dimensional space.
So how does that apply to an AI thinking about a word?
Well, intrinsic dimension measures how many different variables or directions the model is using to represent information. A high dimension means the model is like that bird. It's juggling a ton of independent concepts all at once.
So a low-dimension representation might just be the literal words.
Roughly, yeah. Or a simple instruction. But a high-dimension representation is feature-rich. It's not just holding the word bank. It's holding the idea of river and money, the emotional tone, the grammar, what happened 3 sentences ago. It's a huge cloud of connected ideas.
And let me guess. When they measured this intrinsic dimension,
It peaks right in the middle.
the middle peak again?
It's an almost perfect match. In a model like Pythia 6.9b, the feature richness, the Eitalder spikes around layer 13. And when you overlay the graph for brain alignment, it also peaks right at layer 13.
So the brain likes the high-dimensional state. It likes the complexity.
Exactly. The paper describes this as a two-phase mechanism. Phase one is the abstraction phase. That's the early to middle layers. The model takes the input and just explodes it outwards. It increases the dimensionality, building that rich cloud of meaning.
It's generating possibilities, context, connections.
Yes. But then comes phase two, the prediction phase, or what we could call the collapse.
The collapse sounds dramatic.
It is mathematically, because the model has to give an answer. It can't just output a cloud of concepts. It has to pick the next word. So the later layers take all that beautiful complexity and they crush it down. They compress everything, throwing away anything that isn't absolutely necessary for that one prediction.
It's like that advice for writers, kill your darlings.
That is a perfect analogy. And the key finding here is that our brain's language network, it looks like the ideas, not the cut. We align with the abstraction, not the prediction.
That feels so true. You know that feeling when you have a thought and it feels huge and complete in your head, but then you try to say it out loud and the words feel small?
Words fail me.
Yeah. This research suggests that's physically true. The thought is high-dimensional. The speech is low-dimensional.
And that final compression, that's what the last layers of the AI are doing. They're optimizing for the output, which makes them look less like the thinking brain.
Okay, skeptic hat on for a second. This is a great correlation. Middle layers are complex, brains are complex, they match up. But couldn't it just be a coincidence? Maybe messy noise just looks like messy noise.
The correlation is not causation critique. It's a good one.
Yeah.
The authors thought of this, so they ran a control test. They used something called random Fourier features.
Looks like a band.
It really does. But it's basically mathematical noise that is statistically high-dimensional. It has all the complexity on paper, but it's just random. It doesn't know English. It's just structured static.
And did it check the brain scanner?
Not at all. Flat correlation,
Yeah.
which tells us high dimension alone isn't enough. It has to be learned structure. The complexity has to actually represent language. It's not just noise. It's a map.
Okay, so it has to be meaningful complexity. But did they prove that this abstraction actually causes the brain alignment?
This is where they did something really cool, a brain tuning experiment. They took a speech model, WaveLM, and basically forced it to go to summer school.
Summer school.
They fine-tuned it. They said, okay, model, forget just predicting sound for a minute. We want you to change your internal wiring until your activity starts to look more like this human fMRI scan.
They made it mimic the biology.
Yes. And after the model got good at that, they looked under the hood. And they found that as the model got better at predicting the brain, its intrinsic dimension, that ID dollar metric, automatically went up.
Wow, so you can't fake it. To look like a brain, the AI had to become more internally complex.
Exactly. And its semantic content also increased. It started encoding more actual meaning. This shows a causal link. High-dimensional semantic abstraction is a prerequisite for looking like a human language network.
That's fascinating. It implies that meaning isn't just some fuzzy philosophical idea, it has a mathematical signature. And that signature is high-dimensional geometry.
That's a beautiful way to put it.
I want to touch on the geography of this for a moment. We keep saying the brain, but where in the brain is this happening?
The paper is very specific here. The high correlation spots are the frontotemporal regions. Basically, if you put your hand on your temple, that's the area, the classic language network.
But there was an exception, right?
Yes, the primary auditory cortex. That's the part of the brain that just handles raw sound pitch, volume. That area actually aligned better with the early low-dimension layers of the AI.
Which makes total sense. The early AI layers are just hearing the noise before they make sense of it.
Exactly. Low-level AI matches low-level brain processing. But as soon as you move into the parts of the brain that understand the story, you need those high-ID middle-layer abstractions to get a match.
This whole thing really challenges that stochastic parrot criticism of AI, doesn't it?
It really does. If you only look at the output, sure, it's just fancy autocomplete. But this research says you're missing the forest for the trees.
So?
Because to be a good enough parrot, to accurately predict the next word in a complex story, the model is forced to build an internal world that is incredibly rich and structured. It has to derive meaning to make the prediction.
The prediction is just the test. Understanding is the only way to pass it.
That's it. The mechanism is abstraction, even if the objective is prediction.
It almost makes me feel bad for the AI. It has this incredible, rich, complex understanding in, say, layer 13, and then by layer 24 has to dumb it all down just to pick the word the.
It highlights a universal constraint of communication, I think. Whether you're silicon or biology, you have to expand your understanding to grasp the world, but you have to collapse it to act in it.
So what does this mean for building the next generation of AI? If we want models that are more human-like in their reasoning, should we stop obsessing over prediction accuracy?
That's a huge takeaway. The author suggests we might be optimizing for the wrong thing. If we want AIs that align with human thought, maybe we should focus on enriching that intermediate state, that high-dimensional abstraction phase.
Quality of thought over accuracy of speech.
Precisely. And now we have metrics like intrinsic dimension to actually measure that thinking phase. We can optimize for the journey, not just the destination.
This also seems to open up a wild new door for neuroscience, right? Can
Right.
we use these models to study ourselves?
That's the ultimate hope. It's a tool for in silico experimentation. We can't just go into a human brain and turn off layer 13 to see what happens,
Right.
but we can do that in an AI. We can poke it and prod it and see how it breaks the alignment with the brain data.
It's a crash test dummy for cognitive theories.
Exactly. It suggests these models aren't just commercial products anymore. They're becoming serious scientific instruments.
This has been a massive eye-opener. I feel like we're finally seeing a real bridge between the silicon and the biological.
It suggests that intelligence might converge on a single strategy. It doesn't matter if you're made of meat or metal. To understand a complex world, you have to build a complex, high-dimensional map of it.
So here's the thought I want to leave everyone with. We spend so much time analyzing the output of AI, the text, the images, the code, and we do the same with each other, right? We judge intelligence by what people say or produce.
You judge the collapse.
Exactly. But if the most brain-like state of an AI is in the middle, hidden away before it ever generates a single word, and if our own brains align best with that silent, abstract phase,
Then maybe the truest form of intelligence isn't in the result.
maybe the real thinking happens in the silence. If the machine looks most like us when it's just pondering possibilities, not when it's giving the answer, maybe we should appreciate that middle layer in ourselves a bit more, too.
That is certainly something to think about.
Does the truest form of intelligence exist in the silence of understanding rather than the act of speaking? We'll let you mull that over. Thanks for diving deep with us today.